Cool. Okay, so the presentation is about quantum-inspired FaceNet, and it's quantum-inspired. We are not really using any kind of simulators or quantum computers for this, so just wanted to make that distinction. What quantum-inspired basically means is that we kind of pick the things that we like, and we use it for our own benefits instead of grabbing the full suite of things, and stuff like that. So let's dive into that. So real world facial recognition models, especially the academia ones, they're kind of very heavy. If you look at them, they're the lightest one that I remember is about 20, 30 million parameters. And the idea is that it kind of looks at everything. So what we want to talk about here is that can we teach our model to only look at the significant features and suppress irrelevant ones using quantum interference? And the idea is that in any good facial recognition model, the main thing that it should be looking at is your facial features, not anything else. What your background is, what you're wearing, that's not as significant. So the idea is, can we use sine or wave theory in this case to help us with that?
When you're talking about classical attention, are you specifically talking about vision transformers?
So instead of dot product multiplication, classical dot product multiplication, we're going to be using a sinusoidal transformation over feature vectors.
Okay. So when you say attention, it has nothing to do with visual transformers.
No, it's not. It does not have to do anything with transformer. We're not using the transformer models or anything. Yeah. So this is inspired by quantum interference. So we are going to be using a sinusoidal transformation over feature vectors. And the main important thing is that this function has two parameters that I will dive onto later. It has a scale and a bias. Those are both weight matrices that get adjusted over through training. So here's the overall architecture. Now I know it's very blurry, so I'll kind of breathe things out. So we get our input image, then we have our CNN backbone, which has 4 convolutional layers. So this is kind of the layer where you're trying to get as many features as you can. Then you pass it through a funnel or a filter layer, which kind of gets your 32K size vector into a 16-dimensional vector. So you kind of filter out here what is really important and what is not. And then you basically pass it on into quantum-inspired multi-head attention, just so that the model can learn different aspects of the facial recognition itself. And the entire pipeline is driven by a triplet loss function. So we'll be diving into each one of those in just a second. So in our CNN backbone, we basically have what this basically is that we have our 3 input channels RGB. So this is basically a description of how the image in the data set looks like. And we have our 4 convolutional layers. So notice we go from 64 to 128 to 256 to 512. And the goal of this is to get as many features as we can, as much description about the image as we can, and then pass it along. But before we pass it along, we flatten this out into a pretty high dimensional vector that's the exact size, and send it over to the funnel layer.
Oh, when I'm looking at this, I'm thinking as at the convolutional part, it's like, as you go deeper into the network, the column gets smaller at the y at the base.
Right. So it's kind of getting
really long. So you have like you're flattening out all of the feature spaces into the image input space into a really long feature space.
Vector, yeah, exactly. So the idea really here is that you want to send it to the linear layer just so that it could understand. That's why you have to flatten it out, just to kind of give the reference here. So in this funnel layer, the main idea is that we can send it over so that it's now the main goal of this model is to keep everything lightweight, and I pretty much trained this entire model on Colab. The main goal is to get that 32K dimensional vector into just 16, And this is done using two linear layers plus ReLU. So you could call it the funnel layer or the filter layer, either one works. And the idea is that it over time learns which are the most relevant features. And the main thing is that if you follow this instinctively, this does not know which ones are the most relevant features in the very start. That's why your epoch validation accuracy is pretty low in the beginning. But the idea is that over time, the triplet loss basically adjusts the model so that it kind of understands, okay, this is relevant, this is not. Now you could say that apart from the quantum inspired layers, this has a pretty good contribution to the model as well, because if this did not filter well, we would not have a model learning anything basically. So this is the main aspect of the innovation here. So notice that we have a sinusoidal function, which is basically has two learnable parameters, scale and bias. Now scale and bias get adjusted over multiple training epochs, and the idea really is that it tries to find the right sinusoidal function that that highlights the right features, whereas it destructs the wrong ones basically. And you could notice that we have a small alpha there to regular training. Basically, we don't want the entire sinusoidal function to destruct the entire blocks entirely. We only want to lower its significance, if that makes sense, just so that we are not really erasing aspects of entire feature maps entirely. So why sine? That's basically because periodic function mimic interference, and just to kind of go into trigonometry here. So if we were to think that if our feature vector was 0, it has no information, we don't really want to highlight that. So if you notice, sine of 0 is 0, but cosine of 0 is 1. This is something that I found, this is something that made it really easy for me to understand when I was actually working on this. So you don't want to highlight features that don't really have to be highlighted. That's why sine is a really natural fit for interference. And back to the alpha again, we have a small constant. In this case, we kept it at, I believe, 0.2. But if you're a little daring, you could get that up to 0.5, 0.6. But I would not recommend that getting that to 1, because that would basically be very unstable.
What is the range of alpha?
It's from 0 to 1. I would honestly keep it between 0 and 0.4, just so that it's not destructing entire feature maps, if that kind of makes sense.
You go sine of 0
Um,
is 0? Is sine of 0 0?
Sine of 0 is 0, cosine of 0 is 1.
Okay. And
So
that prevents the values from always collapsing to 0.
right, but that also kind of tells you that if an information is not relevant, you're not really necessarily amplifying it.
Right.
In case of cosine, you're amplifying it, even if it's not significant. But in case of sine, you're not really amplifying it. And it's also, if you go by the books, sine is a way better fit than cosine for quantum interference. So there's that. So this entire pipeline is replicated with, is kind of regulated with triplet loss. So triplet loss, the easiest way to explain it is how close is the image I am comparing to. So supposedly if I have two images, how close the images are to each other basically in terms of facial identity. So if they're both same, but maybe the backgrounds are different, or maybe if we're just talking about me, maybe I have a beard in one picture, no beard in another, maybe something like that, then it would be in the positive space. However, if it's a totally different person, then it would be a negative value. So this kind of drives our entire pipeline to kind of make sure that the facial recognition model aligns meaningful features. So just to kind of build the same intuition here, so supposedly if you're saying if we assume each one of these boxes is an image, I wasn't really sure whether I could use images out of the exact the data set or not, but that would have probably made a better fit. But let's just assume each of these is a picture. The same color means it's the picture of the same person. Different color means it's a picture of a different person or a different facial identity.
Could you say that one more time?
So let's assume that the same colors mean same facial identity,
Okay.
and the different color means it's a different person.
Yeah.
Just because I didn't really know how the Creative Commons, because when I created this presentation, it was a academia conference and they don't really want you to add anything unsighted, so I wasn't really sure whether I could get the pictures out of the exact data set and paste it there. That's why I thought it would be better to do it.
It's fine. But image 1 and image 2 are just different.
They're the comparison images.
Yeah.
This is the ground truth image, if that makes sense.
Okay.
This is the image that I'm kind of saying that, okay, given if I know the identity in the anchor image, how is it, are we talking about the same person or not in image 1 or in image 2? So let's assume the same color means same facial identity, and the different color means a different identity or a different person.
Yeah.
So the anchor image and image 1 aren't necessarily the same exact image.
They're not the same image. I could switch them and name that image 1 and name that image 2. It does not have to be the same. This is just a way of saying.
No, what I mean is they're not the same image, but it's images of the same person.
Yep.
Okay, it's like anchor would be like Bob sitting in a chair, and image 1 would be like Bob playing pickleball.
Yep.
Or like if you go back to the police shows, anchor would be like the mug shot, and image 1 is like the thing from the camera.
Yep. That's another great way of putting it.
So is your anchor supposed to be kind of like your ground truth? You're saying is image 1 the anchor person, is image 2 the anchor person?
Yeah, that's what the entire triplet law says. You basically regulate the entire pipeline based on whether because the way the data set is VGG face, and it has multiple photos of the same person within many different folders. It's actually 3.4 million images, I think. Anyways, so the idea really is that whether are we talking about the same person and teaching that to the model so that it can get certain aspects of the image as well.
Have you ever thought about the kind of how they would like evaluate facial recognition? I haven't thought about this. This is interesting. 'Cause I didn't know that you would need to have like your anchor image and everybody else is the same image of the same person. And if it's a different person, that's clearly wrong. That's your negative right there.
Mm-hmm.
I mean, vectorize it in normal case recognition software. Like you create a vector, and you just compare how similar these two vectors are. Like
Right. That's how the ML models understand it, and that would actually happen to. Let's assume if these were images, that would exactly happen to these as well. But yeah, I mean that's exactly what would happen, and the idea is to kind of reinforce it in the most
like convert it into a multi-dimensional vector.
right. It would be a multi-dimensional vector, and basically the idea is that the model has to figure out that okay, this is the same person and that is a different person, and the model would understand okay, this is what I should be focusing at, right, over time. So basically, another interesting aspect is the images are curated from basically different celebrities, I think, and different aspects or different lightings or different positions, just like he was saying. So if
List
you're
of all of the Real Housewives.
right, exactly. Could you say that again? Uh-huh. Well, that's something that I don't think, because they are within the same time frame, just so that the model can learn. Because I actually tried it. I tried it with an image of myself right now, and 10 years ago. But the difference is between me right now and 10 years ago, there was such a huge difference that the model would get confused. But I guess that could work too, yeah.
Is triplet loss kind of like the
the standard for facial recognition. Yeah.
I wonder if you could build in a layer of like artificial aging of your anchor images to sort of build in that time gap.
That would make it a whole lot complex.
That's all I was just saying. You have to develop the model to do the artificial aging.
Exactly. So it'd be a model inside of a model, more like Inception.
Yeah, yeah. But that'd be an interesting way to keep track
You're
of
like
these
trying to,
models.
well, you're like trying to solve a simple problem by introducing like a more complicated thing.
Plus with celebrities, it doesn't work because they just all
Plastic.
become more plastic, yeah.
Yeah.
Does it work with people who've had face transplants?
That's a really good question.
Because like, to what extent is the face like the skin, and to what extent is it the skull?
I guess I'm not really sure how that would.
Well, when a more simpler use case just be like a two-factor authentication thing?
Uh-huh,
Do they
that-
have
that
the
would
things
be-
where you can log in on your phone or
Mhm.
something?
Well,
And then it's just your face if it captures your face to log in.
so the I am not really sure about this, but I guess the one that we use on iPhones and Android, right? I feel like they're more closed box models in terms that these are more academia models, and in this case, you're using the entire image to tell whether this is. You're using the entire image, and then the model has to learn that okay, this is the face, this is what I should be focusing at. Whereas if it's my phone, all I gotta do is scan it through my place it near my face, and then it basically recognizes me, right?
But ideally, somebody who looks like you it wouldn't work though.
So I actually tried it with my brother, and he looks kind of close to me. Depends on who kind of, but it was more like, I think it kind of gives you a rating on how similar it is. So it gave a rating of 0.75, so 75% facial similarity. And I'm guessing the way it kind of understands is the facial structure. I've heard that's different for everyone. Everyone has a different facial structure and the placement of different facial features. So I'm guessing that's how it understands it, but I guess that's also an answer to plastic surgery too. Unless your facial features or placement is changing, you should be able to get it, but yeah.
You train this on twins?
Twins is supposed to be the same.
So twins, well, it kind of depends. So if it's the identical twins, no, I've not tried with that because I don't know any identical twins.
I don't think we have big of a data set.
Have you ever had a case where somebody killed somebody with the murderer had a twin?
Yeah, I think it happened once. I don't remember that. I was watching it on YouTube.
This is like audience-generated adversarial examples, maybe.
I saw it.
Well, it'd be. I think we could write a new paper on applications of facial recognition based on the questions and kind of submit it. I'm pretty sure they'll find it interesting, to say the least. But anyway, so kind of the same thing. So the value would be positive if we're talking about the same person, and the value would be negative if we're talking about a different person. But the main takeaway here is that I kind of give it credit to two things. So first is the funnel or the filter aspect of the model that basically does pretty much most of the heavy lifting in terms of which facial features the model has to be looking at and which ones not. So that kind of gets the big credit. And then the sign-based feature interference also kind of helps you decide which features or which aspects of the features are important and which ones are not. So the main thing is this is pretty GPU friendly. I kind of trained it on Colab with just the entire research kind of only costed me $10. So I would say it's a pretty cheap model, to say the least, compared to the other models which kind of are at a very high level just for training. But anyway, so if you kind of see how many parameters this model has, this kind of sits at 8.2 million parameters. And compared to the other ones, which the lightest model is about 20 to 25 million parameters, and some even reach to about 50 or 100 million parameters. So that kind of gives you a picture on how lightweight this really is. However, this comes at a cost of accuracy too. So if you look at it, the maximum validation accuracy you kind of reach is 91%. And the facial recognition models, kind of the ones that are really heavy, reach at about 95 to 97%. Now, can we reach to 95% with these parameters? I would say yes, but with a better loss function, something that gives the funnel layer or the filter layer an idea of what it might be getting wrong, as well as the sign-based feature modulation as well. If that also has a customized loss function, I feel like we could, optimistically, I hope we could reach to 95 to 97, but I would say that we'd be expecting at about 92 to 93% just with a better loss function.
Well, you have less parameters if you sign the sign total.
Right.
So how do you know if your loss of validation accuracy is due to the fact that the sign model versus the fact that it just has less parameters? Like, have you done?
Actually, I have not. That's a good question. But the idea was because there was no other model at this kind of level, let's just say 8 million parameters to kind of compare to. We were kind of like, okay, this has 91% accuracy, seems good with the number of parameters that's submitted, and the kind of whatever I'm talking about right now, that maybe we could optimistically reach 92 to 93%, actually came to me after I submitted the paper and it pretty much got published and everything. So would a similar model perform the same exact ARC validation accuracy? Probably, if you're really clever with it. But can you reach higher too? Yeah, for sure. I feel like we could kind of squeeze a few points with Optuna based training, or maybe even a better loss function, to say the least. But that's if I'm being optimistic. It could be that the model has reached its max cap with this, but
Would it be possible to take a pre-existing, like, standard model that's not sign-based and then cut the parameters down?
it could be, but I feel like that would also hurt the accuracy by a lot.
Right. Well, that's totally.
That's
That is the kind of the point. What I'm trying to say is, like, I'm trying to isolate. I would want to be able to isolate if the difference in accuracy is due to a different methodology, how you're computing the weights, versus it's just the fact that you have less parameters.
Yeah, no, that could be a good idea. That could definitely be tried out.
Yeah,
But I feel like at least if you're cutting by 10 on those, oh yeah.
So you said 95 to 97% was kind of what you were looking for, but I mean the main use case for this is like policing, right? So if I was a police officer and I had a description of a fugitive and I saw somebody on the street and I was 90% sure that that person matched the description, could I just arrest that person? You know, it's like what is the actual bar that you can use these things in the real world and like be able to repeat it?
Well, so the reason I'm kind of saying 97% is because I feel like there is a paper that basically said that human facial recognition sits at about 97.5%. So the idea, yeah. So they basically, whenever somebody says that hey, it's 97% accurate or 98% accurate, people are basically saying, oh, it's better than we recognize faces. But so that's where the number comes from. So definitely from an industry standpoint, I feel like this is good enough, but like from an academia standpoint, you really want to improve as much as you can.
But I mean, again, from that legal standpoint, do you know if there are any like pending cases or stuff like against like
I think
police
there's a
organizations?
case, an innocent man got arrested and because of AI, and he got released, but he still has a criminal record. I think it happened like a year or two.
Oh wow, sad to say the least. Yeah.
Probably.
I'm kind of curious, I don't know if you've seen it before, but someone had developed some sort of like walking gait model. So basically, instead of like facial recognition, it basically tracks the body, because most cameras are up high, they can see you, but they don't necessarily have a resolution to see your face. And so what it does is it basically sort of projects like a skeleton as you're walking, and it can sort of identify you by your gait and how you walk, and basically assign you an identity, even though they may not know who you are.
That's more of a behavior fingerprinting, I would say, more or less.
Yeah, but I'm curious if, I'm
It's
curious
like
how
a
accurate you can.
Pose detection model, maybe?
Yeah, pose detection. I'm guessing they probably use something from NVIDIA to do the sort of animation auto tracking, you know, for the joints and things like
Right.
that.
No, to be honest, I'm not too sure about this. Funny you say that. I saw that in a movie. I'm not really sure which
Well,
one.
actually saw it.
Actually, it's already happening.
Oh, yeah.
I saw it the other day. I guess there was a shooting at a Boston college somewhere over there, and someone was using like that sort of thing to try and track who the shooter was. I don't know if they were accurate, but it was interesting.
I feel like, how would you get the data sets out? Because this one is basically based on public information. That's
Well,
my.
you don't need an anchor per se. You just need to watch people for an extended period of time in some busy area, and you know, maybe places where people may come more than once or multiple times, and then you could basically say, oh, that's, you know, subject 24B because he's been here 17 times, right? So even though you don't know who they are, you know who they are when they've come because you've tracked that. And then maybe you could implement something else to sort of assign a real identity.
I feel like
mean, I'm sure they're like,
there no one comes twice, right?
I mean, it's already happened. I mean, not in the US.
No, I'm just curious. I'm just curious how it actually works, because I feel like AI models are pretty good at, if you have data, they'd be pretty good at understanding
So
it.
you could identify people through an ID internal, right? And then maybe you have a different camera set up where you actually get a close-up of people's faces, and maybe you can figure out who they are on LinkedIn or whatever, and then it gets sort of set as, oh, 24B is Joshua, right? And then as time rolls on, you get more of a bigger data set. You're not going to identify every single person, but
you know they're unique.
you know who they are. You know how
You
they
know
walk.
most of the people who live in Brooklyn.
Like, for example, you don't want to catch a particular person. They can use this technology to follow him.
well, I guess the technologies I've heard of are, I think, you like, there's probably something like that in Manhattan, where they have an operations center, and then there's a controversy because, you know, they thought maybe some of the banks were tracking their employees when they left office, or because they had access to the information too. And then there was another thing, there's something called a flock. Maybe they're a startup who do traffic cameras. So they were tracking a lot of information, but then that was also a controversy because they didn't have very good security, or, you know, anyone could access the cameras and like stalk people too, even if they weren't the police. So probably need to be careful with some of these applications.
So big corporations like Walmart, they are definitely using something, probably facial recognition, because even if you go into Walmart and you pay with cash, they can still know what you bought. So there's something going on, probably the cameras at the terminals whenever you go to cash out, things like that. So they know who you are, and they have an ID associated with you. You know.
Yeah, every Walmart register, now that you say it, has a camera that basically, I don't know if anybody has noticed, says this video is recording.
Yep.
So I feel like if you pair that with the amount that, or anything that anybody's getting, you could
Yeah.
pretty much profile everyone.
It's for their own nefarious purposes of advertising, right?
Or just make theft prevention or something.
I'm sure there's other uses for it, but I would assume it's mostly advertisement. They can sell your advertisement data to whoever.
You know you love Oreos.
Yeah, exactly. So now you're going to see nothing but Oreo ads on Amazon. Right?
How long does it take to go through each file? And what's the batch size?
So batch size was, So initially when I started it, I was doing it at 128 batch size, but then I scaled it up to 4092 or 96 because that's the maximum the A100 on Colab could handle. And I wanted to make sure that I was using the maximum, I was using it to the best efficiency as I could and squeeze as many epochs as I could. So my counter hit at 150, and I feel like 150 is probably where you could see that the model is struggling to climb. Now will it climb if you give it another 2 to 300 epochs? Probably, maybe not, but you could probably see that it's barely climbing after 50 to 100. There's what, 1.4, 100 to 150, there's only 0.8% increase in validation accuracy. So so it basically starts converging at, I would say, about at 50, but we kind of keep it rolling for another 100 more epochs. So a smarter, I would say in this case, a smarter training strategy would have probably helped too, in terms of you kind of regulate your learning rate whenever the model is converging, and kind of go based on that. That would have probably helped the model. So yeah, that's pretty much it on this slide. So yeah, so basically the main problem with the facial recognition data sets was none of these models were basically reporting their training and validation accuracy, which I thought was really weird, in terms that most of the other database tasks did report that, but not this one. So most of the models trained on one model evaluated on another, but I did not have a lot of liberty for that. One reason was that these data sets, they take a lot of time. You have to request for them, and then basically you kind of get the data and everything. So there's that. So I actually do not know how much their validation accuracy was. Maybe it was 93, 94. I really have no idea. But it does in terms of, if you look at in terms of parameters, it does outperform them in terms of that it's way lighter, and at the same time it's still good at facial recognition with the computational cost, of course. So I feel like that's it for the presentation. Of course, we have the future work here. So the main idea is to try it on other data sets as well. Geospatial would be another, speech and biometrics is another that I do want to try it out on. But primarily, first I want to actually try out a few more tricks on this model, see whether I could reach it up to 92, 93%. Yeah, that's basically it from my side. I not at the moment, because it will be available in a, because the way this basically works is that I have to submit it to Springer, and Springer releases it as part of their
Actually, your
so-
publisher is not letting you do it.
yeah. So I gotta wait for another
You
week or
can't
so.
just release your paper like a draft for us to see?
I can release my paper, but I gotta go through official channels. Yeah.
So can you share it?
I can actually.
Do you have, so you can't even post your code on like archive?
I actually did submit on a similar archive type repo for code. It should be available in a, I feel like it should be available tomorrow or day after tomorrow, to say the least.
Okay.
But yeah, there is code that you can use. There's actually a trained model weights as well. So if you guys want to try out, you can try it out on that.
Did you use something like PyTorch or something to?
Yeah, so we use Torch, but we did not use transformers. I think we did not use transformers because the entire multi-head attention was simulated by hand, just because it's a different kind of multi-head attention. In terms of we are using sine, not classical dot products, so there wasn't much use for transformers, but we did use Torch.
Okay.
Mhm.
Like as far as like you actually doing the development on it, like
Mhm.
what was sort of the kind of the steps, like were there
Sort of like functions or,
So if you're talking the basics of it, the kind of, I mean, to start, it's on. I basically did the entire thing on Colab, but the entire model is written on Torch. Functions are basically just classes, and each model is a class. So every time you load your data set onto a data loader, then you train it for 100 epochs. But in this case, what I did was I actually saved the, at least in the later training, yeah, whenever I actually saved the training information as well, just so that I could resume it again if I want to. The main reason for that was the first time I ran out of credits. So I got stuck at 70 epochs. So then I realized that if I'm gonna put more um, energy in terms of time, not in terms of cost, but like it still takes a ton of time, or it feel like 100 hours. And Colab does not always keep running; it crashes if you're keeping it running for the entire day. So you do wanna have the liberty to resume if it crashes and kind of stuff like that. I'm not really sure whether the model weights I have are basically the pause and resume kind of one, or maybe they're the regular. I will have to check on that, but I think they're the pause and resume. But I will share the link with you once I get from, I think it's Mentally that I submitted it to, the entire code repo. And I can share the paper if anyone wants to take a look at it.